Welcome to Copilot Podcasts. Imagine calculating something and getting an answer that's off by 120 orders of magnitude. That's exactly what happens when physicists try to predict the energy of empty space. Today, we're diving into one of physics' greatest mysteries, the cosmological constant problem, and a revolutionary new way to solve it using modular mathematics. By the end of this episode, you'll understand why empty space isn't really empty, and how a radical new mathematical approach might finally resolve this massive discrepancy.
And what makes this particularly fascinating is that it's not just about getting the numbers right, it's about fundamentally rethinking how we view vacuum energy itself.
Before we dive in, can you explain what exactly the cosmological constant problem is?
Sure. When quantum physicists calculate the energy density of empty space, what we call vacuum energy, they get an enormous number. But when astronomers measure it by looking at the universe's expansion, they find it's drastically smaller.
How big is this discrepancy we're talking about?
It's mind-boggling. The theoretical prediction is about 10 Hego 113 joules per cubic meter, while observations show it's more like 10 joules per cubic meter.
Wait, that's a difference of 120 orders of magnitude? That's like, I can't even think of a good analogy for that.
Exactly. It's the largest discrepancy between theory and observation in all of physics, and it's been a major problem for decades.
So what's the traditional approach to calculating this vacuum energy?
Well, in quantum field theory, we typically add up all possible energy states in empty space, what we call zero-point energies. It's like summing up an infinite series.
And that's where things go wrong?
Yes, because we're treating vacuum energy as a bulk accumulation, just adding up more and more terms. But this new modular approach suggests that's fundamentally incorrect.
You know, this reminds me a bit of prime numbers. They also have this fascinating pattern that emerges when you look at them the right way.
That's actually a brilliant connection. In fact, this new approach uses something called Gaussian primes to structure how vacuum energy behaves.
Can you explain what makes this new approach so different?
Instead of treating vacuum energy as a bulk field that we sum up, we reframe it as what's called a modular surface transformation.
That sounds complex. What does that mean in simpler terms?
Think of it like this. Rather than adding up infinite energy contributions, we're looking at how energy echoes across curved surfaces, with each echo being filtered through specific mathematical patterns.
So it's more like waves rippling across a surface than filling up a container?
Exactly. And these waves aren't random. They're structured by something called tile exponents and tensorial resonance.
You know, this makes me wonder about black holes. Could this approach help us understand them better?
Actually, yes. This modular approach might help resolve the black hole information paradox because it gives us a new way to think about how information is encoded on surfaces.
Can you break down how this actually solves the cosmological constant problem?
The key insight is that vacuum energy decays logarithmically with what's called prime rarity. The small value we observe isn't a problem to be fixed, it's a natural consequence of how these mathematical structures work.
So we've been looking at it backwards all this time?
In a way, yes. The huge discrepancy isn't a calculation error, it's a sign that we were thinking about vacuum energy in the wrong way entirely.
This seems like it could have huge implications beyond just this one problem.
Absolutely. It suggests that many of our physical theories might need to be reframed in terms of these modular mathematical structures.
What would that mean for physics as a whole?
It could lead to a more unified understanding of quantum mechanics and gravity. These modular structures might be the missing link between them.
That's a pretty bold claim.
It is, but the mathematics behind it is remarkably consistent. When you look at the equations, they naturally connect quantum behavior with gravitational effects.
How testable is all this?
The theory makes specific predictions about how vacuum energy should behave at different scales. We can test these predictions with precise cosmological observations.
What kind of observations are we talking about?
We'd look for specific patterns in the cosmic microwave background radiation and in gravitational wave signals that match the mathematical structure this theory predicts.
And have we seen any evidence yet?
The initial results are promising, but we need more data. The theory correctly predicts the observed vacuum energy density, which is already a significant achievement.
It's fascinating how a purely mathematical insight might solve this long-standing physics problem.
Yes, and it's a reminder that sometimes we need to completely reframe our perspective to make progress.
What are the next steps in developing this theory?
We're working on extending these modular mathematical structures to other areas of physics, particularly quantum gravity and cosmological inflation.
Could this help us understand the early universe better?
Potentially, yes. The same mathematical structures might explain why the universe expanded the way it did in its earliest moments.
This all sounds incredibly promising.
It is, but we should remain cautious. While the mathematics is elegant, we need more experimental verification.
What's the biggest challenge in testing these ideas?
The main challenge is that we're dealing with extremely subtle effects at the cosmological scale. We need very precise measurements to confirm the theory's predictions.
And our current instruments might not be sensitive enough?
Some are, but we need more data. The next generation of gravitational wave detectors and space telescopes will be crucial.
How long might it take to get definitive evidence?
With current technology, probably 5-10 years. But unexpected breakthroughs could speed that up.
That's actually faster than I would have expected.
Yes, and it's because we now know exactly what to look for, thanks to the mathematical precision of this approach.
This really could be a turning point in theoretical physics.
I believe it is. It's not often that a single mathematical insight can potentially resolve such a fundamental problem.
What excites you most about this new approach?
That it might help us understand not just vacuum energy, but the very nature of space, time, and gravity itself.
Those are some pretty high stakes.
They are, but that's what makes physics so exciting. We're constantly pushing the boundaries of our understanding.
Well, this has been absolutely fascinating. We've learned that the cosmological constant problem might be solved not by fixing a calculation, but by completely reframing how we think about vacuum energy, seeing it as a modular surface transformation rather than a bulk field.
Exactly. Sometimes the biggest breakthroughs come not from solving the equation, but from realizing we were asking the wrong question entirely.
And on that profound note, we'll wrap up this episode of Copilot Podcasts. Remember, the next time someone tells you space is empty, you can tell them it's actually full of mathematical echoes. Thanks for listening.